So now I have proved that if you take the minimum value of the function mi or the maximum value of the function in that particular subinterval, in that particular rectangle, ultimately you will reach at the exact value a. Now, but what about if I take any arbitrary value f ck in that interval? So I will prove that also. Suppose I am taking any arbitrary value of the function in that particular delta xk, that in subinterval. So this m will be less than or equal to f ck less than maximum. So multiplying by the length of that subinterval delta xk, this will be less than this thing, less than this thing. Now if I do the summation over all from k is equal to 1 to n, so this thing will be less than or equal to f ck delta xk. This is the old Sn which we are using, arbitrary f ck and arbitrary summation from k is equal to 1 to n. This will be less than or equal to k is equal to 1 mk delta xk. So what I can say that ln is less than or equal to Sn less than or equal to un for all n. Now this is given. Now I know that as when I take the limit n tends to infinity, I know that this ln tends to a. I know this. Similarly, I know that this un tends to a. Then what has this Sn, has it got any other option but to tend to a? By sandwich theorem, because this Sn is bound between ln and un. This ln is telling that okay, I am going to converge at a. un is saying that okay, I will also converge at a. Now this poor guy Sn, which is trapped between this ln and un, will say that okay, ultimately since you two big boys are going to a, I have also no other option but to go to a. So this Sn will also converge to a as under the limit n tending to infinity. So what I am saying, this summation k is equal to 1 to n f ck delta k will be tending to a, will converge to a. That's what I told you initially, that now it does not matter whether you choose mk or this mk or fck, any value in that subinterval, my final answer, that is a, is immaterial of the value of function, the height of the rectangle I have chosen. You can say why this is happening. This is very simple. You see, ultimately what is happening, you are choosing a subinterval and the length of this subinterval is delta. Length of this subinterval, this delta x is equal to, what is this? b minus a by n. We had seen this long ago. As n tends to infinity, this tends to 0. So what I am doing, I am squeezing this subinterval from both the sides, that this subinterval is being squeezed. So if this subinterval is being squeezed, the function value, this small m, that is the minimum, the capital M, the maximum, or any arbitrary, these will also be converging to one point, because as you go on squeezing your subinterval, this function has got no elbow room left. This is equal to limit n tends to infinity f ck b minus a by n, or limit n tends to infinity this thing, and delta x is equal to b minus a by n. If I am taking, say, my interval as 0 to 1, then I can put a is equal to 0 here, b is equal to 1 here. I will get this delta x will be 1 by n, and this thing will become k by n. So if I use in this formula a to b, this will become 0 to 1 fx dx equal to limit n tends to infinity, k is equal to 1 to n, f of k by n, 1 by n. This is the right hand sum. Why? Because I have started my calculation, my counting from k is equal to 1 and finishing at k is equal to n. Same thing I can do if I use the index from k is equal to 0 to n minus 1. In this case, this is called left hand sums, because you are starting your calculation from the very first point a. In this calculation, I am starting my calculation from a plus k by n. So how, you suppose you are given a problem in which summation is there, how to convert a summation formula into an integral formula. If you see this thing, if you say this thing and this, you will know that as n tends to infinity, I have to write instead of 1 by n, suppose 1 by n is given, you convert it into dx, k by n into x. So this k by n becomes x. This summation, this sigma will become integral sign. And what will be the lower limit of integration? You concentrate here, you put the first k is equal to 1, whatever you get under that limit n tend to infinity, put k is equal to 1, whatever you get you put as the lower limit, say a here, or maybe 0 in this case. Similarly, upper limit of integration, you put the last index, the n here, you will get b, and then you put b as your upper limit. Suppose I have to find limit n tends to infinity 1 by n plus 1 plus 1 by n plus 2 till 1 by 2n. So when I write this in terms of this formula, limit n tends to infinity, summation f k by n, 1 by n is equal to 0 to 1 fx dx. I know this thing. So when I start writing this thing, I can write it as, this is same as limit n tends to infinity, summation, I can take 1 by n common outside in all the brackets. So what I will get inside the bracket, I will get 1 plus, because this n will be taken out, so I will get k by n. Now I can integrate this summation from k is equal to 1 to n. So what is this thing? This is limit n tending to infinity, summation 1 by n f of k by n, where my fx is, what is the function I will have to take? Function will be 1 by 1 plus x, because instead of k by n I put x, then I will get the same thing. So what will be this limit? Will be integration 0 to 1, fx is 1 by 1, so this will be 1 by x dx. This will become ln 1 plus x, limit is 0 to 1, you put the limit, you will get answer as ln 2. This is very simple. Same thing in this case, instead of 2n they have put 6n here. So what will happen? This is also not very much different from this formula. In this formula, what I will write now, instead of, this will become limit n tends to infinity, summation k is equal to 1, and instead of n here you will have 5n. Why 5n? Because this 6n can be written as n plus 5n. This 2n was n plus n, so ultimately it will become 1 plus n, 1 by 1 plus k by n, where now your k is going from k is equal to 1 to 5n. Now when you convert this summation into integral, you will get is equal to 0 to this k, lower limit will become 1 by n 0, upper limit, since it is 5n, it will become 5n by n, it will become 5, it will become 1 plus x dx. Now you integrate it, you will get ln 1 plus x, put the limit 5, you will get ln 6. So this is a simple use of integral formula for summation of sums. Another sum, let's see, this sum is for Sn is equal to 1 square by n cube plus this thing. You have to find limit n tends to Sn. Now you have to see that, okay, if I take one of the n outside, 1 by n, what will remain inside will be 1 by n whole square, all the summation square. So ultimately this will be from integral 0 to 1, this 1 by n, this is k by n, so this k by n, the function is x square dx, 0 to 1 x square dx, we will get answer as x cube by 3 or 1 by 3. You may wonder in this problem that only I have got n minus 1 here, whereas for this summation I should be having something like n square by n cube. Very valid point. What you do in this thing, you add also n square by n cube. By adding n square by n cube, you are not adding anything substantial. Why? Because ultimately when you take this limit n tends to infinity, this fellow n square by n cube will turn out to be 0. So if I can add n square by n cube just to make it very smooth summation formula, or I can argue it in another way also. Instead of using k is equal to 1 to n, let me use the left hand sums, which was k is equal to 0 to n minus 1. In that case, what I have to say, instead of k by n, instead of 1 by n, I can add one first term as 0 by n whole square. Now since there is nothing, adding a 0 to any sum will not change that sum, so it will become 0 by n whole square plus whatever is given here, from k is equal to 0 to n minus 1. So ultimately you will get the same answer as 0 to 1 x square dx. So this also shows that whether you take right hand sums or you take left hand sums, it hardly makes any difference, but you have to make sure that these number of k is equal to 1 to n, they should match. There should be like, if you're taking 1 here, then it should be n here, or from 0 here then n minus 1 here, just to make sure that these right hand formulas are correct.